Alright, welcome back. So today is going to be a little different. Video is probably going to be a little longer than normal. Actually, it's probably going to be a lot longer than normal. We're going to spend all our time working through one long specific problem and outlining all the features of it, and giving you some generic formulas to solve this type of problem in the future. And that way, this video works as like a one-stop shop for this type of problem. So the problem reads, Jaden wants to make an open-top box by cutting out corners of a square piece of paper and folding up the sides. The paper is 12 inches by 12 inches. The volume V of x is in cubic inches of the open-top box is a function of the side length x in inches of the square cutouts. Question 1 wants us to write an expression for the volume V of x. Question 2 asks, what is the volume of the box when x equals 2? And question 3 asks, what is a reasonable domain for the volume of the box? And question 4 is, what is the maximum volume the box can have? So straight off the bat, we're making a box, and maybe the way we're making that box is a little confusing. This problem is really popular inside the math world. If you take calculus, you'll see this at least more than once in a calculus class. You'll see it a few times depending on what kind of algebra class you're taking. I know my students keep seeing this problem, and that's why I'm making the video. So let's jump into it. Let's talk about and figure out how we're making this box, because I think once we understand how the box is made, we'll understand where the volume formula comes from and how it works, and then we'll go from there in answering the questions. So we're starting in this problem with a square sheet of paper. So I'm holding up, I should do this. Let's switch to the camera only. So now you get a good look at my face, but better yet, you get a good look at a square sheet of paper. This sheet of paper I'm holding up is in fact 12 by 12. And now the first step, it says, is we're cutting out squares from each of the corners, and those square cutouts are length x. So what I've done is I measured in the corner of this piece of paper, in every corner, I'm going to try and hold it up to the camera. There you go. In every corner I measured out a 1 inch by 1 inch square in all of the four corners of this sheet of paper. And the next thing I did is I cut those squares out. So the 1 inch squares are cut out of every single corner. So all four squares cut out of the four corners. And now what happens is along those black lines, this like top portion, this piece folds up. And we're going to fold up each of the four pieces to give us this, what's an open top box. This looks more like a tray because the sides are so shallow, but there it is, an open top box. And now those square cutouts were all 1 inch squares that I cut out of the corners. And so because that's our x can change, so I did two more examples. This is the same size sheet of paper, 12 by 12, except now I measured 2 inch squares into every corner, and I then cut all of those squares out, and we could see how the shape's now slightly different. From the red 1 inch square, we now have the green 2 inch squares cut out, so you could see when I overlap the cutout pages how there's extra red showing underneath that green because the green cutouts were so much bigger. And so these tabs, these much bigger tabs now, get folded up to look like this green open top box. There you have it. So from this, we fold each of those tabs along the black lines, and we get this box. And now I went ahead and did one more box. So let's take a look at that. Same 12 inch by 12 inch sheet of paper, except this time I did 3 inch squares in each of the corners that are going to get cut out. And when they're cut out, they look like this. So we could compare that to the green 2-inch squares that we had. Slightly bigger. And then even bigger still from the red cutouts. So red were 1-inch cutouts, green were 2-inch cutouts, blue were 3-inch cutouts. And those are all squares, so 3 by 3, 2 by 2, 1 by 1 were the size of the squares cut out. And now, same thing here. I'm going to fold these tabs inward to make, or not inward, but upwards, to make a new box. And so now let's look at all of these boxes inside of each other so we can see how the shape has changed as we changed X. So hopefully we can see that the blue's taller than the green is taller than the red, and also the overall size, going the wrong way on my camera, you can see how the blue is length and width is shorter than the greens, shorter than the length and width of the red. So what I want to talk about is some of the dimensions of this on camera before I start drawing it on my whiteboard, so that you can kind of recognize what's happening and see where some of the dimensions are going as we do this. So I'm going to use the blue square, the blue box, because I think that's the easiest to see because there's such a drastic difference. So if I was to open it up, from this top piece to this bottom edge, hold it way back, is 12 inches, because that's the original length of the paper. And from this edge to this edge, that width is 12 inches, because that's the original piece of paper. And now this cutout distance, right in here, these two edges are both length 3, which would be our X. And if you notice, that length becomes the height of the box as I fold it up. As I fold up that box, that distance of 3 becomes the height of my box. And as I go from the length of 12-inch original piece of paper and fold in those sides, the length of my box becomes the leftover amount after I make those cutouts. So here's the original width, or length in this case, because it's a square. And when I take 3 away from the one side and 3 away from the other side to fold it to make the walls of the box. So all those ideas you kind of want to keep in mind as we tackle number 1 to this question, which was write an expression for v of x. So I want to take time and write an equation for the volume of this box, but now in terms of x. And we want to keep all those things in mind, that the cutout distance gets folded up to be my height, and that the original length takes away both sides to become the length of the box shape. And the same thing with the width. The original width minus the left and the right sides to be the length or width of this box. So we're going to talk about that right now. And I'm actually going to talk about it in terms of length and width and not use the numbers from the problem, so that we create a general formula for this type of problem, so that if you find a problem where the rectangle sheet of paper is 10 inches long by 6 inches wide, you could still use the same volume formula that I create. You just got to plug in the appropriate numbers for the length and width. So let me clear some paper out of my way, and let's get to it. So now we're back at the whiteboard, and I'm going to move the problem over here to my left, or to my right. Well, it depends on, I don't know, maybe it's just my right. And so question 1 says write an expression for the volume. So let's create a, let's make sure we don't do that again. So here it is. Here's a sheet of paper. Oh, is this gonna be too close? I don't know. We're gonna have room. Or should I do, you know what, we're gonna do this. We're gonna zoom out a little bit so that my paper can be bigger and I can put more detail in it. So here's my sheet of paper. Kind of crude, but you get the idea. And so what we're gonna do, or what we have been doing, is we've been cutting out squares in each of the corners. And so we're cutting a square out from each corner. And so this is going to go bye-bye. Both of these, all four of these corners go bye-bye. And now the length and width of that square was x by x. Each of these is x. So all four sides of these boxes and all four corners are all length x, because that's the measurement of the cutout. And now what's left is that plus sign. If you're looking at my camera, actually I'll change to my camera. So after we make the cutout, we are left with this with the plus sign shape. And we're going to fold these tabs that are sticking out along this black line that I have drawn on my pieces of paper. So looking back at our picture, we have lines going here and here and here and here, and we're going to fold those green lines, fold along those green lines, and we're going to fold these tabs upwards. So let me just write tab in each of these. These tabs all get folded. So that's how we're making the box sort of in a two-dimensional display of it. So what we want to do now is create a formula for this box. So this is going to be our length. Actually, let's not do that in green. We want to do that in blue, or not blue, black. So this whole thing is the original length of the piece of paper. And then down here, this whole distance is the original width of the piece of paper. But now, if you remember from my camera display, and I'm going to go back to it, that the original length gets folded along those lines, and those green lines from my picture are the new length and width of those creases, are the new length and width of my three-dimensional box. So looking at the inside of it, those fold lines become the new length and width of my three-dimensional box. So going back to our whiteboard, that new length and width is in here. Is right in here. This is the width of the box. And then this is the length of the box. So we just got to create a, I don't know if I like using L and W again. Maybe we need to use, maybe I'll just say L of box, L of box, and width of box. So those blue length and widths are the lengths and widths of the actual box, but I want to use the black lengths and widths because that's the distances I actually know, because that's the size of the paper. So I want to figure out what those distances are in terms of the original length and width and x. So actually, let's erase these, because we can fill in with the expression that is the new lengths and widths of the box from the original length and width of the piece of paper. So this middle distance right in here is the leftovers from removing those squares. So this blue distance is the full black length minus the amount that I cut out up top and the amount that I cut out on the bottom. And each of those are x's. So that blue distance is the length minus an x from the top and minus an x from the bottom, which is the length minus 2 x's. That middle distance is left over once I've subtracted and cut out 1x from the top and 1x from the bottom. And that width on the bottom is the same thing. That's this middle width is the original w minus this x distance and this x distance, because it's the leftovers. So the width of my box is going to also be the width minus 2x. So the width of my box is w minus 2x, and the length is the length minus 2x. So the width of the box, w minus 2x, the length of the box, L minus 2x, the length of the piece of paper. Now we've got to figure out the height of the piece of paper. And to show that, I'm going to go back to my camera. And remember that we started out with this flat sheet. Where'd that piece of paper go? We started out with this flat sheet of paper and then cut these squares out of it. And when those squares were cut out, we had this shape. We had this plus, well, it's too flimsy now. We had that plus sign shape. And that amount of cutout in the corner gets flipped upwards to be the height. So this distance that was cut out, gets folded upwards and is now the height of the box. Well, the distance of that cutout is exactly x. So let's make sure we write all this down. Where should we write it? I'll write it over here. So the length of the box, is L minus 2x, the length of the sheet of paper minus 2x. The width of the box, ooh, that W is kind of ugly. Let's try again. The width of the box is W, the original width of the piece of paper, minus 2x. And then the height, as we just talked about, of the box is exactly the amount that we cut out. Oh, you cannot see what I'm writing right now because I didn't move back to my whiteboard. So I've just wrote this stuff in black right here. The length of the box is the original length of the piece of paper, L, minus 2x. The width of the box is W, the original width of the piece of paper, minus 2x. And that height of the box is exactly h. So now those three things together, length times width times height, are all going to give me the volume of the box. And that answers question 1. Volume in terms of x is equal to the length of the box, L minus 2x, times the width of the box, W minus 2x, times the height of the box, which is just x. And that's all in terms of L, the original length of the sheet of paper, W, the original width of the sheet of paper, and then x, whatever the cutout is. So for this particular problem, my length and width were both 12 inches long. So it would give me 12 minus 2x times 12 minus 2x, because I'm working with a square piece of paper, times x. And so this is my answer for question 1, where they wanted me to find the volume of the box. We wanted an expression for that. So there it is. Now, we could pause here for this original problem, or if you're working on a different problem, I can show you real quick how we can keep this original formula, and all you need to do is trade out the L and the W for your length of piece of paper. So if you had a standard sheet of paper that was 8.5 by 11, your formula for your volume using a standard sheet of paper would be 11 minus 2x, your length minus 2x, times your width minus 2x, times your height. And so that blue formula would be for a standard sized sheet of paper. So every time your length and width of your material changes, your L and your W will change with it. Now I'm going to keep going with the problem I have. Number 2 asks us, what is the volume of the box? Ooh, I don't want blue anymore. I want to switch back to black. Kind of color code things in terms of our problem. So number 2 is, what is the volume of the box when x equals 2? So that means if x equals 2, I want to find v of 2. And so that means everywhere in my formula, in my expression, that there was an x, I'm going to replace it with the number 2. And that gives me, oh, my handwriting is a little crooked. So that gives me that v of 2, oh, having a hard time seeing that on my screen. V of 2 is equal to 12 minus 2 times 2. That blue 2, of course, is my x right up here. We want x equals 2. And then times 12 minus 2 times the blue 2, which is my x, times 2 again for the height, because if my cutout is 2 inches, that makes the height of my box 2 inches. And now I go from here, following order of operations and simplifying. So I need to do the multiplication inside those parentheses first. So black 2 times blue 2 gives me 4. Black 2 times blue 2 also gives me 4. And that 2 on the very end sticks around. And now I need to do the subtraction inside those parentheses. So both of those are 12 minus 4, which is 8. Giving me 8 times 8 times 2. And then we need to multiply 8 times 8, a nice perfect square of 64. And then now we can multiply by 2, and that gives me a volume of 128. So that is the volume when x is equal to 2. So this is v of 2, the volume when x is equal to 2. Alright, I'm going to scroll back up for question 3 now. Question 3 asks, what is a reasonable domain for the volume of the box? Alright, we're going to do this over here. And we'll write the question down so we can keep that on the screen. Domain for v of x. Now, x is a distance, which, because it's a distance, and specifically it's a distance we're cutting, X shouldn't be negative. I don't know how to cut a negative 2 inches. I don't really understand what that means. So in this context, positive distances make sense. Maybe, perhaps, if we were using an X coordinate system where our piece of paper was centered on that and we were talking about that sort of thing, you could possibly refer to a negative distance. But in this context, a negative distance doesn't make sense because it's just the amount that I'm cutting out of the piece of paper. And so for that reason, X should be greater than 0. Because it's a distance, we should cut something. If I don't cut the piece of paper at all, if I don't cut this sheet of paper at all, I won't have any tabs to fold up because that distance that I'm cutting out then creates the tab to fold. So if I have no tabs to fold, I literally can't make a box. That's another way to think of it. A cut of 0 means there's nothing cut out, which means there's no tab to fold. So just another way to think about it in terms of this problem. Now, the tricky part is thinking about how big of a distance we can go. So we're going to go back to thinking about a digital piece of paper here in 2 dimensions. And so this is our length of our paper, and this is the width of our paper. Let's kind of fix that L. That L's kind of sad. Now, when we're cutting from the bottom, from all of the sides, and from the top. And we're making like 2 cuts in each place. We're cutting in on those red lines to cut out those squares. And so as the distance gets bigger, let's do a different color now. Let's make it purple. If we do bigger cuts, then we cut, obviously, even more paper out. And we've got to think about how big of a cut we can make. And what should or shouldn't happen. For instance, what happens if these cuts meet? If I make one cut and then another cut over the same piece, and then make the same cut here and the same cut here, what happens to my piece of paper? Well, part of the problem is that there won't be a tab left over here. We've now cut away any kind of tab that will be folded up to make the side. If we look back at our sheet of paper, if I make this square cutout too big, this tab will not exist because I can cut it like this much, and then I cut it, this much. That middle tab will fail to exist, and that tab is what literally creates a wall, or all the walls really, of my box. So we got to think about how big can I go? How far in can I cut before the cuts meet? And that simply boils down to how far in can I go from 2 sides. I'm coming in from the left and the right on my sheet of paper. Let's draw a new sheet of paper over here. So here's my sheet of paper. Length, width. I don't want my cuts to meet. So if I cut in from the left and the right, these cuts cannot touch, because as soon as they touch, then that piece of paper is cut and there's no, well, obviously it's cut, but it's cut into 2 pieces and I don't have a tab anymore. So I got to think about how far in I can cut. I also should think about which distance limits me, the width or the length. And the answer to that is the shortest side, which is often referred to as the width of the piece of paper. The shortest side of the piece of paper is what's going to limit you. If your length is 15 inches and your width is 10 inches, the 10 inches is going to be used faster in total compared to the 15. For instance, if I were to make 4-inch cutouts from each of the corners, 15 minus 8 gives me 7 inches left over, where 10 inches minus the 8 inches of cutout only leave me with 2 inches left over. So that 10-inch cutout, or that 10-inch side, is going to get used the fastest, and the width is going to get used the fastest. So what we need to think about is how far we can make 2 cuts, one from each side on the width. And they're going to meet up in the middle, so we can only go halfway on our width. That's the biggest cut we can make, is half of the width. So our domain over here is going to be the width of my piece of paper divided by 2. That is the biggest cut that we can make without ruining the piece of paper and having no wall to fold up on our box. If we go any bigger than the width divided by 2, we'll have cut that sheet of paper into 2 pieces. So there you go. That's the formula for the domain. The width divided by 2 is the largest x can be, and 0 is the minimum. For this particular problem that I'm working on, my width and length are the same. So in this case, my width is 12, and that gets divided by 2 to give me my new and proper domain, 0 less than x less than 6. So x should be somewhere between 0 and 6 in order for me to make a box. Whew, that was quite a bit. Now, the very last question. What is the maximum volume the box can have? And to answer that question, I accidentally grabbed the words when I wanted to just grab this. What is the maximum volume the box can have? That question can be answered by graphing the equation for the volume. So we're going to go ahead and do that now. So I'm going to head over to Desmos. There it is. Desmos is great for graphing. DESMOS.com, and it's pretty simple to use. To start, I just need to type in this left-hand toolbar the equation for my volume, which as soon as you start typing, it starts graphing. So this is the equation for my volume. And it immediately starts graphing it in red. I am going to adjust it slightly. I'm going to adjust the y-axis so that it shows us better values. So I'm going to go from, I don't think negative 50 is too high. We can go from negative 10, try 300. Let's try 200. No? Yes. Perfect. And let's actually add, we're going to go negative 50 to 200. There we go. So this gives us a beautiful picture of our volume, which you can't see because my head's in the way. There it is. I'll move it so you can see it better. So this red graph graphs the volume for us. And what I want you to notice is along the x-axis. Well, so first, 2 things to notice. This red line obviously represents the volume, and where it dips below the x-axis back here represents a negative volume. I don't know what a box with a negative volume would look like, so it's a good thing that we start the x values we're looking at 0, because to the left of 0 gives us a negative volume, which we can't have. The other thing I want us to look at is how at 6, which was the maximum distance we came up with for x, our volume is also 0. So another thing to keep in mind, that our work previously was right, and actually if you don't feel like doing the math that we did for your particular problem, you could always type in the equation you create for your volume and then take those zeros to help you see the domain for your particular box problem. Obviously, the distance of 0 is almost always going to be there for your x, but then this largest value that x can be is going to be the next time it touches the x-axis. So we're looking between 0 and 6 for our maximum volume, and Desmos does an amazing thing. It always marks where our relative minimums and maximums are on the graph, so it gives us a point right there on our graph, and sure enough, our maximum volume happens at x equals 2, and that maximum volume is 128, which I've already calculated. That's like a coincidence I didn't think was going to happen when I created this problem, but there you have it. So going back to number 4, the maximum volume is 128, and now that's inches cubed, because we're working in a 3-dimensional space with volume. So this video's been pretty long. Showed you how to create the volume of the box, the expression for the volume of the box with L and W, the original length and width of the sheet of paper. Specialized it for my 12 by 12 inch piece of paper. Showed you how to substitute in a value for your volume to find the volume. I showed you how to create the domain, which for this particular problem is going to be from 0 to your width, the shortest side, divided by 2. For me, that was 0 to 6. And then we also went to Desmos, and I graphed the function to find the maximum value. All things you can do. If you have questions, please leave them in the comments for me, and I will see you next time.